All right, fantastic. Well, welcome everyone. This is Introduction to Sparkvue, and I'm looking forward to sharing with you some of the key techniques for collecting data and analyzing it in Pasco's Sparkvue software. The agenda for today is quite busy. I have three activities planned, but I welcome your questions throughout if you're joining us live. The first activity is going to look at the essentials of collecting and analyzing data with Sparkvue and a little investigation of how coffee cools. So I'll pose a little scenario in a moment and ask your predictions for that, and then we'll learn how we can connect sensors to Sparkvue, collect and analyze data. Then we'll look at how we can vary how we're collecting data in another experiment where we're briefly looking at the collision of a cart with a barrier and seeing if we can analyze the forces involved in that collision that are happening quite rapidly. Finally, we're going to take a look at a new way to get data, a new technique called manual sampling. We'll also take a look at taking control over our collection of data in a technique called manual sampling and build our own pages. That's going to be an investigation of the relationship between gas pressure and volume. So I'm going to go fairly quickly through these, but again, I welcome your questions, and you'll have the recording to refer back to if you want to walk through any of these at your own pace. We will pause occasionally to answer your questions, although Heidi will be taking care of many of those questions directly in the text window for Q&A. And we'll talk about saving files, the supported platforms for Sparkvue, various sensors supported by Sparkvue, and experiment resources where you can get labs that are ready for your students. So I'm going to kick it off with a scenario here, and we'll take some measurements and see if Sparkvue can help us answer this. So imagine that you're headed to school. You like coffee a lot, and you stop at a coffee shop that's pretty close to your school before you reach school to begin your work day there. You get a cup of coffee, and say your walk or your drive to school is 3 or 5 minutes. So it's a pretty short commute between the coffee shop and school. But you have a little dilemma in that the coffee at this shop is great, but it's really hot. It's lawsuit hot, and you happen to like a lot of cream in your coffee. So you're wondering one day, what can you do with this cream to make sure the coffee cools down enough in the 3 to 5 minutes it takes to go from the coffee shop to school? So you can imagine there are two possibilities, right? You could add the cream to this very hot coffee at the coffee shop and then walk or drive to school for 3 to 5 minutes. And you'd arrive at school with a coffee cup full of cream and coffee that has cooled somewhat between leaving the coffee shop and getting to school. There's another possibility though. What if you just took that black coffee at the coffee shop and you took it with the side of cream, room temperature cream, and you waited until you got to school 3 to 5 minutes later before you added that cream? You'd end up with, again, cream and coffee. But which of these two would cool the coffee the most? So the question we'd like to answer is to cool your coffee the fastest to make it drinkable at school. It's too hot at the coffee shop. Should you add the room temperature cream at the coffee shop or at school? So, those of you who are joining us live, I'd love to get your opinions on this. So, make your prediction here in the poll. I'm going to ask you to make a prediction. It may be based on information or just a guess. Which approach do you think will cool the coffee fastest? Add the cream immediately at the coffee shop or wait and add that room temperature cream once you get to school? So the votes are coming in here. Thanks for your participation. Even if you're not certain, feel free to make a guess there. And as before, I'll share the results once we get most of them in. All right, leave it open for about 15 more seconds. And by the way, the things you see on the screen here are the cup that we'll use for some hot coffee in a moment, along with the cream. And I will be adding cafe au lait proportions of cream here, though. But unlike cafe au lait, it's going to be at room temperature. Great. Thanks for your responses. Let me go ahead and share the predictions. And wow, it is a exact tie. Half of you think adding the cream immediately at the coffee shop is going to cool it, and the other half think adding the cream at school is going to cool it the fastest. So we have some controversy here. I'm glad. So we can go ahead and get some data and try to analyze it to answer that question. So let's talk a little bit about the equipment I have to do this. I have a wireless temperature sensor. This is one of Pasco's wireless sensors, and I'm going to show you how we can connect this to Sparkvue to collect data from it. So let me jump over to Sparkvue, and once you launch Sparkvue, no matter what platform you're on, more about platforms in a moment, you can choose a path. What do you want to do with Sparkvue? And some of the most popular paths are along the top here. The one we're going to focus on for this activity, and indeed the next one, is we want to collect some data. So the sensor data path says allows you to connect your sensors, choose measurements and displays. That's exactly what we want to do with this temperature sensor. So I'm going to choose the sensor data path. And then once we get to this sensor data configuration screen, I'm going to turn on the power to my wireless temperature sensor. I just pressed the power button for half a second. When I did that, the battery light blinked for just a moment, and then I see a steady blinking of the Bluetooth light at the bottom. Now, if you're here with us live, you can change the relative size of the live video on my screen if you want to see the details of the video a little bit better. There should be a handle between those two sections. But if you can see it, you'll notice that this Bluetooth light is blinking red. That means the sensor is available to connect, but it's not yet connected. Now, in the classroom, you hopefully have a number of sensors. So I'm going to turn on a second temperature sensor. You may notice the temperature sensor showed up here in the panel to the left of Sparkvue's sensor data configuration screen. So a little further away, I'm going to turn on a second temperature sensor, and you can see that appears as well. And the second temperature sensor is also blinking red in its Bluetooth light. Now, our programmers were clever. The sensor that is closer to the computing device, that is probably your sensor, is going to be the one show up at the top of the list. And if you want to confirm that, you can simply look at the ID that's on your sensor. So if I look at my sensor, both of them are indeed pretty close to the computer I'm using. I can see that it has an ID 962-548, and that matches the one at the top of the list. So if I want to connect to this sensor in order to be able to collect data from it, I'll go ahead and click on its name in the list of available devices. Sparkvue is going to connect to it via Bluetooth 4 wirelessly, and you can see it moves up to the connected devices portion of the list. This sensor is no longer available for anyone else to connect to since I've connected to it. Now, to speed this experiment, I'm actually going to buy 2 cups of coffee at once. And these 2 cups of coffee will allow me to kind of repeat the conditions quite well. Thanks, Eddie. And I'm going to use this second temperature sensor as well, which gives me the opportunity to show you that we can indeed connect more than one sensor at a time to Sparkvue if we want to make multiple measurements. So let me click on the name and number of the second temperature sensor, 779-136. It is going to move up into the connected devices portion. And we can connect multiple sensors if we want to make multiple measurements. So in this scenario, I'm going to buy 2 cups of coffee at the same time, hopefully at the same temperature. And we are going to go ahead and make those measurements of cooling, comparing the instance where I've added cream at the shop and I've added cream at school. We could do this experiment with just one temperature sensor as well if we wanted to. All right. So Heidi, any questions while I set up the coffee here?
Yes, actually, we had a question about how many sensors you can connect. And I know we can connect up to 4. Some I've seen up to 6, depending on the software use. But we also have sensors that have several sensors built within them, like our weather sensor that can take up to 19 measurements.
Indeed. How many actual sensors you can connect is kind of a function of the Bluetooth radio on your computer. It's always going to be at least 3. It can go up much beyond that. But as Heidi just noted, some of our sensors, like the smart cart we're going to get to shortly, have 11 measurements built into one sensor, and others, like the weather, have something like 17. So I'm going to mix these 2 hot cups of coffee, imagining that we're at the shop here. And I'm going to go ahead and put in my temperature sensors into the hot coffee. So imagine us buying 2 cups of 2 hot coffee at the coffee shop. And as soon as I connected the sensors here in Sparkvue, you can see that they populated this center column. I'm going to leave the temperatures checked. I'm going to choose this table and graph display in the upper right. And now we can see it constructs for us the displays I requested. We have a table of time, the temperature measurement from the sensor on your right, and another column here, the third column, the temperature sensor on your left. And then we have 2 plot areas inside this graph showing each of the temperatures on the y-axis and a shared time. Now, I'm going to look down here and I can see that there are live readings of these 2 temperatures down here. I can see that the -548 sensor, which is on your right, is at 74.8, and the sensor on your left is at 75.1. So pretty close to each other. I'm going to go ahead and imagine that we want to now start recording data. And as soon as I press this green start button, you're going to see the data from both of these sensors populate the columns of the table and also be displayed here on the graph. And we can see that when the data reaches the end time there at 10 seconds, the graph just automatically rescales to ensure by default we are seeing all of the data being collected. So I'm going to pick one of these 2 cups to add the coffee to, imagining that we're just leaving the coffee shop here. I'm going to choose the 136, which is on the left. And here will be our sample where we add coffee at the coffee shop. Go ahead and take a look at the graph as I add that room temperature cream to the coffee. And we can see what appears as a green run here is rapidly decreasing in temperature. Now, it's a little tough to see both of these. We can change our scaling in the graph even while the data is being recorded. So imagine we're hopping in the car now, or leaving the coffee shop if we have a walking commute, and we're headed towards school with these 2 cups of coffee. the one on the bottom graph showing what happened when we added the cream at school, at the coffee shop rather, the one on the top showing the we haven't added the cream yet scenario. So what we can do with the graph while we are still collecting data here is we can rescale it. So if I grab my cursor and put it over the numbers on either the x-axis or either of the y-axes, you can see that sort of like a sheet of rubber, I can adjust the scaling of the graph. I can take my cursor and just go in the middle of the graph, and you can see that I can move it around. So in the middle of the graph, I pan it left and right, up and down. And if I grab the numbers, I can scale it as if it's made of rubber. Now, oftentimes the goal is just to fill the screen with data. So we have something called the graph toolbar. Every display has a toolbar. There's a button that will open and close the toolbar. And in the case of the graph toolbar, the leftmost button, if I hover over it, tells us that that is the scale to fit button. So if I click scale to fit, what's going to happen is Sparkvue is going to analyze the data here and say, if I rescale the y and x axes to the maximum extent of the data you have, we can fill the screen with the data. So scaling options are nice. Usually Sparkvue does a pretty good job. We'll notice when the time is exceeded on the right here at 140 seconds, that the graph is going to automatically rescale so that we can ensure that we're seeing the data being collected. So we are now at a little over 2 minutes since leaving the coffee shop, so we're going to let it go a little bit longer. One thing that makes it a little difficult in this case is I have two plot areas. Both of them are showing temperature, but they have very different scaling. Wouldn't it be nice if we could kind of combine these two into a single graph? Sparkvue chose to just do them separately, which is nice if you have, say, temperature and pH or position and velocity. But when we have two measurements of the same units, I like to kind of put them together on the same plot area. Now, the following is a little bit advanced, but let me just show you it's possible. I'm going to click on the lower plot area and remove it from my graph. And then if I go to the graph tools, you'll see there's an opportunity for me to add another y-axis. I'm going to click on that, and it says select a measurement for the second y-axis. I'll open it up, and I want to choose not the -548 temperature sensor, but the -136. So I can see both of these overlaid on the same set of axes. Now, you'll notice a little bit of a problem here in that the scaling is different, but there's a graph tool that can allow us to fix that. It is called this button right here, Keep Origins Aligned. And when I click on that, we can see both of these aligned on each other. So we have a shared vertical axes now, and we can more easily visually compare these two. Well, it's been a little over 3 minutes. Let's say our commute is a bit short today. So I'm in a moment going to add the cream to the coffee on the right, and we'll see which one is going to end up with the cooler temperature now that we're arriving at school. All right, so we'll give that a moment to mix. And although they started off a little bit different temperatures, we can see visually that it looks like they're going to end up with an even greater gap here. So I'll let that mix a little bit more before I choose to end data collection. You'll notice what was a green start button initially is now a red stop button. And all the data I collect between pressing start and stop is a run. And this legend shows us that it's called run number 1. So I'll go ahead and stop that now. And I'll press scale to fit so we can see that data. And I think right now we can see that even though there was a little bit of a gap here, it looks like when I added the cream at school, that it got cooler in the end after this 3-minute commute. So think about why that might be, whether you see evidence that might explain it here. And as you think about that, what I'd like to do is show you some of the tools in Sparkvue's graph that we can use to annotate our data so we can remember what happened, analyze it to try to answer some of the questions that you have about it. So think about why the coffee might have cooled faster if I was carrying it without the cream from the coffee shop to the school. If you have any suggestions, go ahead and put them in chat. But in the meantime, what I'd like to do is show you some of the tools that will let us annotate this data. We've already seen that we can use scale to fit to fill the screen with our data. I'm going to show you now the annotation tool. I'm forgetful, so if I saved this file and came back in a couple of weeks, I might have forgotten what I did. So I'd like to annotate and note when I added the cream in each of these cases. So the letter T is for adding an annotation. It pops open a window that lets me say that I added the cream. And when I press OK, it is going to attach that annotation to one of the two measurements that I have here, either blue or green. Now, it happened to go to blue. That's fine. We'll talk a little bit later about why that happened, but you'll notice that it just plops it in the middle of the plot area here. I can move the label if I wish. I can also move the point that it is attached to. by clicking and dragging this gray box. And wherever I release that gray box with my mouse, it snaps to the nearest data point. So I think in this case, it would be best to drag it over here, and I can say that I added the cream here. And in fact, I know in this case, this is where I added the cream at school. So I'm going to go and click on this label again and choose that little pencil because I can amend it here. I'm going to say this was added the cream at school. All right, so we've annotated one data point in the blue run. I'd like to do something similar for the green run where I added the cream at the coffee shop. But if I just go back to this annotation tool, I'm going to type some gibberish for a second, notice that it applies once again to the blue measurement, the temperature sensor on the left, where I added the cream at school. That's not what I want, so I'm going to go ahead and delete that annotation and show you something really important when you have multiple runs of data in Sparkvue's graph, or as we have here, multiple measurements of data. And that is the graph legend shows that one of these two measurements is active. The active measurement has a red box around its symbol. That means that the tools that I turn on from the graph toolbar, like the annotation I added a moment ago, are applying to the active run. If I want to make the other temperature measurement active, all I need to do is click on its symbol in the legend. And now when I add another annotation tool, in this case, added cream at coffee shop, we will see that because the green measurement was active, this annotation applies to it. So really important when you have a fairly complex setup like we do here of multiple measurements, or if you have multiple runs. Now, one of the things I haven't shown you yet is that we can just nudge this left and right, but since I have to move it quite a bit, I'm once again going to grab the gray box and let it snap to that point right there, which I think is pretty good. If I want to zoom in to really position it, we could use our manual scaling and panning, and I could say that's where I added the cream at the coffee shop. I'll press scale to fit to zoom back out. So the annotation tool, you can add multiple annotations per run, is a great way to mark what has happened at various points in the data collection process. All right. So ultimately, we might want to quantify this data. I think we can answer our question already. Exactly 50% of you were right, as was inevitable, that adding the cream at school seems to have resulted in cooler coffee after 250 seconds here. So what we might want to quantify, well, how much did the temperature change in each of these cases? So I'm going to note that I have the green measurement active, and I'm going to come down here and introduce a new tool. It looks like a little crosshairs, and it's called the coordinates tool. If I add the coordinates tool with the green measurement active, you'll see that it adds what looks like an annotation, but the beauty of this annotation called the coordinates tool is that as I move it around, notice that the annotation automatically updates to show me the X and Y coordinates of the point inside the gray box here. So I can move this around, I can scroll through. I'm gonna put this at the very beginning of my data. So I'll grab it and snap it to the leftmost data point. And this tells us that at 0 seconds, the temperature for that temperature sensor of in the green run was 75 degrees Celsius. So I probably want to do something similar to figure out the final temperature. I'm going to add yet another coordinates tool, and I'll drag that to the very last data point, and we can see that after 252 seconds, it was down to 54.9 degrees Celsius. By the way, I can't think very well in hundreds of seconds. So if you're interested, you can go to what is the label for the x-axis, time in seconds. You can click on it and you can change the units, or indeed you can change what's being shown here. I'm going to change it from seconds to something I can think of a little better, minutes. And now you can see that all those coordinates tools update to show me that at 4.2 minutes, the temperature had gone down to 54.9 degrees Celsius. So if I wanted to figure out, well, what was the net temperature change for the green measurement here, I could do the math. Or it turns out Sparkvue's coordinates tool has a great tool hidden inside of it. I'm going to remove this second coordinates tool and focus our attention on the leftmost coordinates tool here. And if I click on the label and release, you'll notice that besides the nudging arrows, it has a tool built in that looks like the Greek letter delta. And this may remind you of change, delta for change. So if I click on the delta tool, I basically am given a second handle for my coordinates tool, and I can drag it out and drop it on any point. And you notice this gray shading has little labels on the side that tells me for this point to this point, the change in time was 1.375 minutes and the change in temperature was negative 18.2. So I'm going to drag that out to the final data point there and snap it there. And this very quickly does the math for me. I can see that the temperature decreased by 20.1 degrees Celsius during the course of that for the measurement where I added the cream at the coffee shop. So of course I want to do something similar for the other measurement. So I'll make it active. I'll turn on a coordinates tool. And we have to remember that this delta tool is hidden inside the coordinates tool. So let me grab the gray box there, click on the label for this blue measurements coordinates tool, click on delta, and it's going to get a little busy, but I can see in dragging out this here that the temperature change was just a little bit greater, 21.8 degrees of cooling versus 20.1 for the measurement where I added the cream at school. All right, so let's see. Do you have any thoughts in chat for why the coffee that didn't have any cream in it while I was commuting to school resulted in a greater temperature change? Marie suggests, thank you, Marie. Marie says more surface area to cool in the two containers. All right. If you have any other thoughts, go ahead and put them in the chat there. Thanks, Marie, for sharing that idea. So that was an assertion about different surface areas in these two containers. You can see I went to a very science-focused coffee shop there. I had beakers, but that might be even more exaggerated, different surface areas if I had a non-right cylinder cup. Nice. All right, if you have any other thoughts, feel free to share them. If you don't have any thoughts, take a look at the graph of data here and see if there's anything striking about it. Is there anything subtly different about these two scenarios, especially while I was commuting? All right, Travis suggests something. Travis says in the chat, greater differential in the ambient temp for the hotter cup. Ah, interesting there. So we're talking about the difference in temperature between the coffee and its surroundings, which are definitely going to be much cooler, right? This room is probably somewhere around 25 way down here. So Travis is asserting that something about the greater temperature difference between the blue measurement and ambient temperature versus the green measurement. Interesting. All right. Julia notes there's also convective loss with air. Yep, we can try to figure out was that very different for the two. Robert says hotter cup lost more heat while you were moving. Ah, interesting. So that's kind of along the lines of what Travis was asserting. So let's go ahead and analyze that a little bit more. To keep my graph from being too cluttered, I'm going to remove both of these delta tools by clicking on their blue X's. And I want to focus on that time where I was traveling, commuting. And if you just look visually, do you notice any differences between the blue measurement and the green measurement during the time from about 1 minute to 3.5 minutes when I was going from the coffee shop to the school? Well, you might notice one of them does look a little bit steeper, which is kind of consistent with the things that Travis and Robert were saying in the chat. So of course, there are tools we could use to analyze this. I could put a delta tool on each of these, but I'm going to take this opportunity to show you something new, and that is we could find the slope, a representative slope of this entire region here for both of these two measurements. So I'm going to make sure I have the blue measurement active in the legend, and I'll introduce you to the linear fit tool, which has this scatter plot with a straight line going through it. And I'm going to turn on the linear fit for the blue measurement and scratch my head for a moment here. It is doing a linear fit, but it's doing a linear fit to the entire portion of the data. That includes the portion when I was commuting, and it includes when I'm at school. If I'm only interested in analyzing with the linear fit the data between 1 minute and say 3.5 minutes, I need to be able to tell Sparkvue's graph that, hey, don't analyze the entire portion with the linear fit, just analyze what I'm interested in. And I have a bit of a dilemma because my cursor by default is not a selector, it is a mover, as we saw earlier. But I can use one of the tools in the graph toolbar to change my cursor into a selector. It is this toggle called the toggle move select mode, and you'll see that the move mode is the default. So if I click on it, it will change to select mode. And now I can come out and click and drag a box, and you notice a couple things. This box is adjustable, and all the data points inside the box for the active run are highlighted yellow. And most importantly, this linear fit live adjusts so that it is analyzing only the data inside the box. So you can imagine I might want to do the same, making the green measurement active, turning on, making sure the select tool is there. And by the way, not only can I turn on the linear fit and then make a selection, I can do the reverse. I can make a selection and then kind of conveniently some tools pop up that match the tools in the graph toolbar, including linear fit. And now I might compare, say, the slopes represented by M of the hot coffee as it was commuting and of the slightly cooler coffee because I'd added cream earlier. And there we can see the rates are significantly different, almost a 3x difference, right? Minus 0.65 degrees Celsius per minute for the coffee with the cream in it already versus minus almost 1. almost minus 2 degrees Celsius per minute for the hotter coffee. So I think Robert and Travis may be onto something. Not to say Marie and Julia aren't. Those are further explorations we could make. But I find this is typically consistent that the hotter the thing is, that is, the greater the temperature compared to room temperature, the faster it cools. All right. So by keeping our coffee hot for the longest amount of time, we were able to get it to cool more. All right. So let us know in the chat or Q&A if you have any thoughts or questions about this introduction to Sparkvue, especially the graph analysis tools or extensions for this particular investigation. While you're doing that, let me tell you a little bit about Sparkvue software. So I've been showing you Sparkvue on Windows, but in fact, you probably wouldn't be able to tell because Sparkvue runs pretty much the same. Everything you've done so far runs the same, whether you are on a Windows computer or a Mac computer, whether you're on a Chromebook, an iOS smartphone in your pocket, an iPhone, iPad, or Android phone or tablet. So Sparkvue is available and runs pretty much the same for sensor connection, data collection, and analysis across all of these platforms. It's good to note that you can get Sparkvue on Chrome OS and iOS and iPad OS and Android for free. The full featured app is free in the respective app stores. And for Sparkvue on Windows and Macintosh computers, there is a licensed installer. There's also a free trial. And we also have some devices that are data loggers with Sparkvue built in. If you're interested in learning more about Sparkvue or want to get links to these free apps or trial versions, you can go to pasco.com/Sparkvue and learn some more and see the download links for these. All right. So we've collected some interesting data here in Sparkvue that I might want to preserve. So I'd like to talk about a couple of ways that we can preserve the data and share the data, beginning with what I think is the most important, and that is we can save the entire file, everything about it, from the data to the configuration to the analysis that we've done. And we do that by saving a SparkLab file that will have the extension .spklab from Sparkvue. Let's see how we can do that in Sparkvue. I'm going to go to the main menu, sometimes called the hamburger menu in the upper left of Sparkvue. And if I click on it, you'll see that one of the options is to save. And when I do that, it gives me the opportunity to save this file. At this point, you can see I'm on Windows, so the saving opportunities are going to be different depending on the platform. So I'll say that this is the cooling coffee data. And it's going to save it as a .spklab file. I'll save it to my desktop so I can easily retrieve it. And now if I say end my lab period and close Sparkvue and head over to my desktop, I can see that there's the SparkLab file. And I can either double click on that or I can relaunch Sparkvue. And from the welcome screen that we earlier chose the sensor data path on, I can choose to open a saved experiment, direct to the desktop, and there I can see my SparkLab file. And when I open it, you'll see that it has preserved everything about the lab, and I could continue collecting more data or doing further analysis if I wish to. So saving a SparkLab is a great way to preserve everything about it. And in case you're curious, if I save my SparkLab on a Windows machine, I can share it with anyone who has Sparkvue, whether they're on Windows, Mac, Chrome OS, iOS, iPad OS, or the Android platform. A quick note, this is one place where Sparkvue differs a little bit. If you're on a phone or tablet, you're going to find that you can most easily share a SparkLab file with a dedicated sharing button. I'm on Windows, so I don't have it, but that sharing button is going to show up here in the top bar to the right on iOS and Android devices. All right. So we've covered a lot about Sparkvue. You probably won't remember all of it, but you have the recording to help you review it. We also have a great resource called Sparkvue Help, and I'm going to show you how to get to it. Ultimately, it is on our website at help.pasco.com, but it is also linked to from Sparkvue's main menu that we just visited. So I'm going to go to the main menu and choose Help, and Sparkvue is going to open up the website at Sparkvue Help on my browser. I've just brought that into view. And here you can do things. I like to search. I might say, you know what were those graph tools we covered? So I'm going to scroll down, graph display. And here you can see a nice calling out of all the features of the graph that we covered, including ones that we didn't quite get to. So take advantage of the help for you and your students. Talk about some more resources a little bit later. All right, Heidi, before we continue, any questions that we should address?
No other questions
Okay.
have been coming in. Oh, wait, one just did. Can the data be exported to an Excel file?
Julianne, thanks. You've segued into the next activity beautifully, and I will answer that. The answer ultimately is yes, and I'll show you how to do that after the next activity. Thanks, Julianne. All right. So we've looked at the sensor data path for quickly connecting a sensor, or in this case, multiple sensors, getting some displays, collecting and analyzing data. You also saw me open a saved experiment that I'd saved as a Spark Lab. So we're going to jump over to the next activity here. And in this one, among other things, we'll answer Julianne's question about other ways to get data out of Sparkvue. So for this, we're going to look at a completely different sensor. This is indeed a sensor. In fact, it's a bunch of sensors in the form of what we call the wireless smart card. So this has a bunch of sensors built into it, but they act just like wireless sensors, just like the temperature sensors that we just looked at. So my question here is, I'm going to pose this scenario. I have an inclined track here, and on the end of this smart cart, I have a hard spring. And more importantly, it's attached to a force sensor that's built into the smart cart. So among the many measurements the smart cart offers is a measurement of the force. Let me illustrate our scenario here. I'm going to release the cart from a known point on this inclined track. I'm going to let it collide with that end stop at the bottom. And I'm interested in what sort of forces are applied to the cart while it was colliding in that very brief instant of time with the end stop. So again, I want to measure the forces while that cart and its hard spring are colliding with that end stop. So that's the scenario we're going to pose. We want to figure out, can we accurately capture those forces even if they happen quite quickly during a short collision? So I'm going to head back to Sparkvue. I'm going to close Sparkvue here, and that will disconnect from my temperature sensors, giving me the opportunity to relaunch Sparkvue. And I'll go ahead and choose the sensor data path once again. Now, the smart cart is a basically sensor suite on wheels. So when I choose sensor data, I'm going to turn it on with its power button, just like I turned on the wireless temperature sensors. And in a moment, we will see that it has a Bluetooth light that's blinking red, and it indeed shows up here as an available sensor. And I can identify it by its 6-digit ID and connect to it. And once we connect to it, we'll spend a little bit more time on this center column that comes up to see all of the measurements that the smart card offers. Many of our wireless sensors offer multiple sensors. The temperature sensor offered only one, but things like the weather sensor, the color and light sensor, and this smart card offer many measurements. Each of these blue lines is a sensor built into the cart. So we have a position sensor that measures the rolling of the wheels, and it offers position, velocity, acceleration. The force sensor is what we're really interested in here. It offers measurements of force. And we even have a 3-axis accelerometer and gyroscope built into the cart. In this case, I'm interested in force. As I said, I want to know what forces are involved in that collision of the cart with the end stop. So I'm going to check the measurement that I want to see. All right. Force is selected, and I'm going to go over and choose a template. This time around, maybe the digits and graph template. And it's going to look and see that force is checked in the center column. So when I choose the digits and graph template, it's going to choose force for this digits display and force for the y-axis of the graph. And by default, every x-axis of the graph will be time, although you can always go in and change that if you wish. So I'm simply going to press start in a moment and let the cart roll down the track. And I'm going to ask you to judge whether, with these default settings, Sparkvue is doing a good job at recording the data we're interested in, which is what forces does the cart experience during the collision. So I'll press start, release the cart, let it collide, and I'll press stop. I'll scale to fit and ask for your opinions in chat. Do you think this accurately represents the forces of the cart during the collision? While you're thinking about that, let us know in chat. You can see that we have force on the x-axis. The force did change from 0, it was slightly off from 0, and then it went negative to about negative 6.5 newtons. Why was it negative? Well, the smart cart has a XYZ axis label on it, and we can see that positive X is down the track in this case. So the force applied to the cart was in the opposite direction of that, and that's why it had a negative sign. All right. Thank you, Renee, for sharing your thoughts there. So Renee wonders, do we need more sampling? All right. So Renee suggests it needs more sampling. Yeah. So if we look at it, we see that there's only one data point right here that seems to represent a data point collected from the force sensor during the collision. If you don't know, is that appropriate or not? One thing I often like to do is say, well, is it repeatable? So I'm going to put the cart here back at the same position up the track, and I'm going to press start once again and release the cart again. All right, I'll press stop. And you'll notice for this first time when we've collected 2 runs of data, this is the first time we've done that, you'll notice that run number 2 is there in green, but run number 1 has disappeared. It is not gone though. If I look at the legend, you'll see run number 1 is still listed. It simply doesn't have a checkbox in what we call the visibility checkbox here. So I could look at both at once if I wanted to. And here I can see that, well, still we got just one data point during the collision and it's different. That should be a pretty similar collision because I released the cart from the same point up the track. So I'm a little dubious about this. It feels like maybe we're not collecting enough data. So I agree with Renee's opinion there that maybe we need to sample some more data. Julianne asks another question we'll get to shortly about area of the graph as well. So let's try to fix this sampling issue. If you have any other criticisms, questions about the data we've collected, feel free to share that. But for now, I'm going to show you how to address Renee's suggestion of collecting more data. So I'm going to go in here and notice that if I turn on a coordinates tool, I see that this data point's at 1.2 seconds. The next data point's at 1.25 seconds. So it looks like this data from the force sensor is being collected every 0.05 seconds. And I can figure that out another way. If I look in the lower left, there's something that says periodic 20 hertz. 20 hertz just means that at 20 times a second, or every 0.05 seconds, it's collecting another data point. If I want to change that, I can click on this dial to open what's called the sampling options dialog. And here I can see, you know what, 20 hertz might not be fast enough. Let me increase it. And it seems like the limit here is 500 hertz. If you were interested in doing long-term experiments, say with a weather sensor, you can go slower and you can collect data, once an hour for say the wind speed or temperature. But I'm going to go to the far right here and I can see that I can choose sample rates of 500 hertz. So let's see if that helps at all. So I'm going to set up my cart at the same position up the track. Remember now, as we can see in the lower left, the measurement is going to be recorded at 500 hertz. So I'll press start. Get a little warning here. The system cannot keep up with the sample rate, and it gives us some tips. Try lowering the sample rate for one or more sensors. There's a good reminder. Remember, when I connected the sensor, we don't have just measurements of force. Even though I chose to look at only force, all those measurements you saw, all 11 of those measurements from acceleration to gyroscope to the force sensor and wheels, all of them were recorded. So one of the things we might consider when we're sampling very quickly is, do we really need all the measurements? Here are all the measurements I could be showing right now, and I don't really need those all. So I'm going to go, and I could have done this when I was setting up the lab in the sensor data path, but I'm going to go under the show hardware setup, and I'm going to say we definitely want force to stay on. I don't care to record acceleration or gyroscope, so that gets rid of 7 measurements. I may or may not need position, velocity, acceleration. I'm going to leave those on and see if this still works. So now I go over here and I can see that the force sensor can actually go even faster because I've turned off measurements I don't need. So I might say for position, maybe that's not going to change so fast. So maybe 50 hertz, and I'm going to leave force at a kilohertz. So that's 1,000 samples every second. Let's see if that solves our problem of not getting many data points during the collision. Now, before I do that, one other thing you may have noticed is that the force before the collision and after the collision wasn't quite zero. It wasn't large, but it was a little off of zero. That's because with the cart in this orientation, we have the opportunity to define what the force is. And I can say, you know what, I want this to be zero. So one place we can do that is to go down here in the live data bar, which is not just a readout, but it's also interactive. And if I click on it, you'll see some options. I can change the sign of force. I can actually zero the sensor now. So once I've done that, the live data bar shows us that it's now reading 0 in the current orientation, which is probably what I want before and after the collision. So now sampling at 500 hertz for the force, let's go ahead and press start. I'll release the cart, hit stop. And now if we zoom in to the collision region here, you'll see that instead of collecting just one data point, we collected maybe a dozen or 2 data points during that collision. So I have much more confidence that this accurately represents the forces during the collision of the end stop on the cart. Right. The key there was going in and changing the sample rate, which in the case of the smart cart here required us to turn off some measurements that we didn't need. Now, Julianne's asked a couple of great questions. One of the questions is, can you measure the area of the graph? And that's a great one for those of you who are teaching physics, for example. And the answer is yes. So let me show you a way we can do that. If you teach physics, you may know that as the impulse. So the area, quote, under the curve for force versus time is impulse. And the way we can do that, it's a bit odd, but if we go into the statistics button, the Greek letter sigma, we'll learn that statistics can give us any or all of these measurements: the minimum, maximum, mean, standard deviation, count, which is the number of data points. It can also give us the area. So I'm going to turn on area. and it's going to shade the area between our data and the y equals 0 axis. And if I scale out, you'll see it's actually doing it for everywhere. And if I want to, we can use that same technique we did with the linear fit earlier. And I can say, you know what, I only want the area, quote, under the curve, in this case, above the curve, for this region. So I'll turn on my selection mode. And now I can drag a box out. And I can see that it's shading only the area between the y equals 0 and the data here. And I can see that's negative 0.42. What is that? Newton seconds, right? So that is the impulse in this case. So great question, Julianne. To extend that, if you're interested in impulse and momentum relationship, a more advanced topic in physics, we could, for example, add another plot area. And because I left the position sensor on, we could look at the change in velocity over that same time period. Before the collision, here was the velocity. Delta tool gives us the velocity after. And if we know the mass of the cart, we can relate the change in momentum of the cart to the impulse or area under the force time curve. So a little variation there for those of you who are into physics. If you are into engineering design challenges, looking at just the force of the impact on the cart is a great way to ask students, you know what, could you design something that would decrease that maximum force if you imagine this to be a vehicle, not just a cart, and you want to make the collision safer for occupants. So some neat engineering design challenges spring out of the same thing. The key idea here, though, is that we can change the sampling conditions, in this case, the sample rate, for something like the force sensor on the smart cart. All right, so we're going to get to Julianne's other question in just a moment, but Heidi, before we do, any questions coming in that we haven't addressed? All right, great. So Julianne asked the question, can data be exported to an Excel file? Indeed, it can. So let me talk about the next way to save and share from Sparkvue. And that is we can export the data from Sparkvue into a format that can be opened in a spreadsheet program. So it isn't an Excel file per se, but it is a file that can be opened in pretty much any data analysis package, from Excel to Google Sheets to more complex data analysis software. So thanks for the question, Julianne. Let's go ahead and see how we can do that. We're going to export the data from our Sparkvue file. Once again, this option is in the main menu, and you'll see there's an option to export data. Now, by default, it's going to save it as a CSV, which is short for comma separated value, which is a very common data file that pretty much any analysis package can open. If you prefer, you can change that to a tab delimited text file, but I'm going to save it as a CSV file, save it to my desktop, and I'm going to call this cart collision data. All right, so I've saved that as a CSV. I'll go to my desktop. On my computer, I happen to have associated CSVs with Excel. So I'll double click on that. It's going to open in Excel. And I want to emphasize what we have and don't have here. We have, for all of the runs, we have all of the measurements recorded from the sensor. So it is a wall of data here for run number 1, these columns, run number 2, and so forth. So this is great if you just want the data from the sensors and want to do your own visualization and analysis. What it doesn't give you, though, is any of the visualization that you made in Sparkvue. So the graphs aren't there. Of course, you could recreate those in Excel if you wanted, and the analysis isn't there. But if you ever just want the raw data from the sensors, you can choose to export data there. Thanks for that question, Julianne. All right, so we've taken a look at changing the frequency of measurement with sample rate. We've turned off measurements that we don't need, which is great for multiple measure sensors. And again, as I mentioned earlier, we could do that while we're setting up the data, or we can do it after the fact. All right, I know we figured out that this live data bar is more than just a display. We can also use it to do things like zeroing sensors. For those of you who teach chemistry, you may be interested in often calibrating measurements using the same pop-up menu for things like pH sensors. All right, a little bit more about sensors. So far, I've been using sensors from our line of wireless sensors that use Bluetooth 4. We've looked at the white temperature sensor. In a moment, we'll take a look at a wireless pressure sensor as well. It's white. The smart cart's a bit of an exception in that it is a genuine wireless sensor, but it's going to be either blue or red. So we can do things like, say, the blue cart collided with the red cart. But in the case of all of these, the techniques we've learned for the smart cart and temperature sensor apply across the board. We connect them directly inside Sparkvue. We don't worry about the connections to the operating system, and that allows us to connect in Sparkvue, ensuring that we have the same experience across platforms. Sparkvue, though, crucially works with all of the sensors Pasco has made since, well, the last millennium. So in 2001, we started a line of sensors called Passport that took advantage of the ever-increasing USB ports at that time that were new. These translucent blue sensors are called passport sensors. In this case, we're looking at a motion sensor from each generation of sensors. And those passport sensors still work with Sparkvue. Sparkvue still supports them. It's important to note that you can't plug these sensors directly into the computer. They'll need an interface. But if you're interested in more information on interfaces, in a moment, I'll show you a URL to get that information. And we can even, in Sparkvue, support the sensors that were created in the last millennium, sensors that came out in the 1900s. So sensors probably older than most, if not all of your students, and perhaps some of you. But those sensors can be used with an interface. The Science Workshop it's called, and those black sensors go through an interface, or indeed can be used with passport interfaces with an adapter. But if you want information about any of these sensors and the interfaces required for the two lines on the right, please visit pasco.com/sensors. Heidi, thanks for pasting that in the chat. All right. Well, we have 12 minutes left, and thankfully, this last activity where we're going to introduce some new concepts is a quick one. And hopefully, you'll be impressed by how quickly we can answer the following question. Given a wireless pressure sensor, you can see here, and a confined set of gas, which you can see in this syringe, can we determine a relationship between the volume of this gas in the syringe and the corresponding gas pressure on the sensor? So the question is, we know we can measure the gas pressure with this wireless pressure sensor. How can we measure the volume? Well, I don't have, at least on hand, a sensor that can do that, but I could take advantage of the fact that this syringe, which happens to be included with the wireless pressure sensor, has some markings on it, the volume in milliliters. So if I'm the other sensor, we can measure pressure from the pressure sensor, and I could enter what we call user entered data, which is the corresponding volume. But there are a couple of techniques we need to learn in order to be able to do that in Sparkvue. So let's jump over to Sparkvue and see if we can answer this question. What is the relationship between the gas pressure and volume? So I'm going to close Sparkvue once again. Let me go ahead and save this file as a Sparkvue file just so I can preserve it. So this is the cart collision data. Remember earlier I exported the data, but if I really want a record of everything so I can reopen it and analyze it in Sparkvue, I might want to save it as a SparkLab file, which I typically do. All right, I'll close Sparkvue and relaunch it. And let's connect to the wireless pressure sensor and see what measurements it offers. In fact, we're going to do things a little backwards this time. I want to take you down a path that gives us a little more control of what we're seeing than the sensor data path that we've used so far. I'd like to show to you the build new experiment path. This is going to give us control over what we're seeing. So when you choose the build new experiment path from the welcome screen, you basically get a list of possible layouts, kind of like PowerPoint shows you what layouts are supported in a particular template. So I'm going to choose a layout here that has a small thing on the left and a big thing on the right. We'll see why in a moment. And as soon as I choose that layout, Sparkvue creates a SparkLab file for us with that layout. And notice that it's up to us to choose what displays are in each of the portions of the layout. So in this case, I'd like to create a table display on the left because tables are great for a limited number of data points. Unlike the first activity where we had hundreds of data points for temperature, we're only going to have a few for the volume and pressure here. So I think a table is particularly appropriate, especially for typing data. And on the right, I'm going to use our trusty line graph here. Now, because we're creating our own file here, choosing the build path, we are in control of what measurements are being shown. And if I choose select measurement, you're going to see that, I have a little problem here. I haven't yet connected the sensor. The sensor data path let us do that from the start, but in this case, I need to conscientiously choose when to connect the sensor. And I can do that by remembering that my wireless sensors connect via Bluetooth. There's a wireless sensors button in the upper right. And if I turn on my pressure sensor, we should see it show up here in the list of available sensors. By the way, if you're using a wired sensor, instead of connecting wirelessly, you would simply plug the sensor into your interface, ensure that your interface is on, and that would be an available measurement in Sparkvue if you're using Passport or Science Workshop sensors, or indeed some of the wireless sensors that can also be connected via USB to your computer directly. So I've connected my pressure sensor. And now if I return to the columns of the table, I can see that I could make the second column pressure. I could make the y-axis pressure. I'm not really interested in time. I'm interested in pressure versus volume. So how do we fix this? Well, the most direct way is just to say, you know what? Begin typing the volumes you want to use in the appropriate column in the table. So I'm going to stretch it out to 60 milliliters, and I think I have time to measure about every 5 milliliters as I compress the air in the syringe. So I know it gets kind of tough pushing it, especially with one hand. This is a good two-person experiment, but I know I can go down to about 15 before it gets too tough to hold the syringe. So I've entered my volumes, and what's really neat is Sparkvue said, oh, if you're entering data, that must be user data. You can click on this pencil and tell Sparkvue, hey, these are actually volumes, and you get to choose the units. Since the syringe is marked in milliliters, I'll define the user entered data as volume in milliliters, and that would be a great time. Now would be a great time to change the x-axis from time, which I don't care about, to volume, but I don't see volume here. Well, that's because user entered data ends up in its own tab, and I can choose the volume here. So I have a table now, volumes and pressures, pressure versus volume in the graph, and it feels like I'm ready to start. Let me see. If I press start, ooh, let's see what's happening here. Well, I got a bunch of pressure data. It filled the graph here. Why did that happen? Well, if we look back at our newly learned periodic measurement here, the pressure sensor was set by default to sample at 20 hertz or 20 samples per second. So as soon as I hit start, it did just that, gathering 20 more samples every second. That's way too fast for me to change the volume. So let me delete that. I'm going to go over here to what's called the experiment toolbar, manage runs, and delete the last run, and show you that to do experiments like this, where we're associating user entered data with sensor measurements, we have a completely different mode of sampling that we can access, once again, via sampling options, and it's called manual sampling. So I'm going to turn on manual sampling in contrast to the default periodic sampling. And when I turn on manual and hit start, I have all the time in the world, because notice it is measuring the pressure. It's being monitored and it's telling me it's currently 100.9. It shows me where that data point would be in the graph, but it's not recording it. Manual refers to the fact that I can manually choose when to record a data point. So I'm going to go to place the syringe at the first marked volume here, 60 milliliters in row number 1. So I'm at 60 milliliters. And when I'm ready, there's a green check mark here and here called the keep button. And I can simply check it. And the current pressure sensor reading will be recorded. It turns black to indicate it's been recorded. And since our time is short here, I'll quickly go through. Here's 55 milliliters. Here's 50 milliliters. Here's 45. By the way, if you ever make a mistake, like double counting 45, um, you can go to the data point here and correct it. It looks like I might have been off by 5 milliliters here. So let me go ahead and go back to 60, and we can recollect as long as we haven't hit stop. So there's 60, 55, 50, 45, 40. And even though we're manually collecting data, you can see that I can control it when I record the data here, 35, 30, and the data is being populated live there on the graph. So I can begin to see the shape of this curve relating pressure on the x-axis to volume on the, pressure on the y-axis to volume on the x. All right, so this often confuses students. I've gotten all the volumes and pressures I want. Why is this extra data point here? Well, it's being monitored. You can see it's live. And as soon as I say stop, all the data I collected between pressing start and stop is my run of data. I can see it here in the graph, and I can scale that. And if our question was, what's the relationship between gas pressure and volume, we might want to explore those curve fits again. Is it linear? That doesn't look so good. Well, there are more fits than just the linear curve fit. They're all here in this curve fit, general curve fit button. I can go in and choose linear, quadratic, power. In this case, I might guide beginning students to say, well, is it linear, inverse, or inverse square? So we saw it wasn't linear. Inverse square, that's much better than linear. We could use the shape of the curve visually to determine it, or we could look at things like the root mean squared error. Error lower is better. So let's remember this, 9.74 for inverse square. I compare that to inverse 2.14, and it looks much better. So it looks like we've discovered an inverse relationship here between the pressure and volume just by collecting a few data points with the syringe and the pressure sensor rather in the included syringe. And we've been able to do an inverse fit and discover this law. So I want to show you one more way to get information and share it from Sparkvue, and that is you might want to share an image of your discovery in a graph. So the easiest way to do this, in my opinion, is to take a screenshot using your operating system's screenshot tools. Here are shortcuts to some of those. Since I'm on Windows, I'm going to choose to press Windows, Shift, and S. And if I do that while in Sparkvue, it gives me a little cursor that allows me to do a screen grab of this part. All right, it's now in my clipboard. And now I could go and say, you know what, I'm going to have my report here in Word. And I can paste that image from the clipboard. And here is my discovery of the relationship between pressure and volume. All right. So of course I could save this file as a SparkLab file if I wanted to be sure to come back to it and gather more data. But there are three ways for sharing and saving data. The ones I use the most are on the far left, a complete record of the file as a SparkLab file, and on the far right, taking an operating system screenshot and putting it in something like Word or Google Docs. All right, so that was the build path. It gives you control over the configuration of displays and what exact displays you're going to see. So we've looked at how we can do our own experiments in Sparkvue, taking the sensor data path, the build path, but I want to assure you that even though we've been focusing on Sparkvue's tools, there are a lot of experiments out there that are student ready for Sparkvue. Students, of course, could build your own or you could build them, but there are many included in Sparkvue. So if I go back to Sparkvue and I go to start new experiment, my pressure sensor is still connected. And if I happen to have taken the sensor data path, if you look over here for select wireless sensors, we have experiments built into Sparkvue. And hey, one of them happens to be Boyle's Law. There saves me most of the work I just did. It's already in manual mode. It already has the volumes and pressures set up and so forth. So built into Sparkvue are some things we call quick start experiments. Also built into Sparkvue are a couple dozen Spark Labs, we call them. So I'm going to go back to Sparkvue, start new experiment. And if I choose to open a Pasco experiment, there are a couple dozen here, and one of them is volume and pressure. This is still a Spark Lab file, but it is multiple pages. It gives students background information, has instructions alongside the data displays, and has instructions alongside the data collection. So crucially, even though there are instructions and places for students to answer questions, it's alongside the data collection and analysis displays that we've been learning about this entire time. Finally, these are a few dozen experiments. We have over 1,000 experiments available in our free online experiment library at pasco.com/free labs. In the next minute, let me just show you how we can use that very quickly. So if we go to pasco.com/free labs, or if you want to get there from the pasco.com home screen, you can go to Resources, Experiment Library. And there are over 1,000 experiments in here, so it's important to be able to search and filter. So if I say Boyle's Law, and filter, it gets down to about a dozen. And I can further refine this by saying, what if I'm teaching high school, say, chemistry? Filter that. There are two of them. And what if I'm using wireless pressure sensor? That gets me down to one of them. And this has a set of student-ready files that you can hand out to students or edit. So PDF is ready to print. The Word doc is ready to edit if you want to tweak it. And if you sign in with a free account, you can get the teacher versions of these files. And this one happens to also have a video showing the data collection that we created during the height of the pandemic when schools were closed. So lots of resources. Not all labs will have all of these resources in the experiment library, but you're always going to find some variety of student files, always editable if we can provide that to you. All right. So we reached the end of our time together. I want to thank you so much for joining us today. I'm going to go ahead and end the recording, but if you ever have questions for Pasco technical support, or you want to contact your local Pasco rep, whether in the US or across the world, you can go to pasco.com/support. So with that, I want to thank you for joining us in the recording